Okay, we're on page 6 of the Polynomials booklet. Just a continuation from the first lesson, zeros of a polynomial. Now the conjugate root theorem, we looked at this in the complex numbers topic, and it just states that if a polynomial in Z has real coefficients, okay, so for example this polynomial here has real coefficients, okay, the coefficients of the Z's are all real numbers, and if you substitute a plus bi, which is a complex number, if that is one of the roots of the complex number, a plus bi, if you substitute that in and you get 0, where b does not equal 0, in other words, it has to be a complex number because it has an I component, then if you substitute a minus bi into the polynomial, then you'll also get 0. Now this is the conjugate root theorem. In other words, if a plus bi is a root, then a minus bi is also a root. So therefore, complex zeros of real polynomials occur in conjugate pairs. So this is a complex zero because it has an imaginary and a real component there. Now, if any of the coefficients are not real, so if the coefficients of the polynomial are not real, then the roots will not occur in conjugate pairs, and we saw this in complex numbers in the complex numbers topic. Now we can prove this as follows. Proof of this theorem. Now the conjugate of Z1 plus Z2 is equal to the conjugate of Z1 plus the conjugate of Z2. We also know, so this is separate to this, and the conjugate of Z1 times Z2, so the conjugate of all of that, equals the conjugate of Z1 times the conjugate of Z2. And another rule of conjugates is that the conjugate of Z and all of that to the power of n is equal to the conjugate of Z to the power of n. So using those three rules, okay, let's make sure you divide those up. Let's look at our proof. Now if we've got this polynomial where x to the power of n is your highest power and then just coming down, so a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way down to a to the power of 0. If z is a root, then if you substitute z into the equation, then by substituting z in where the x is, if you put that in, it will equal 0. Because remember, when you substitute a root into equation, by the factor theorem, okay, you'll get 0. Now, if we look at the conjugate of z and substitute that into the equation, you get a sub n conjugate of z to the power of n plus a sub n minus 1 conjugate of z to the power of n minus 1 all the way down here to a to the 0. Now we know from this theorem up here that the conjugate of z to the power of n is the same as the conjugate of z to the power of n here. Okay, so just instead of conjugate of z and then to the power of n is the same as z to the power of n and then the conjugate of that, and just doing the same there. And this is z to the power of 1, so that just stays the same. Now, if you just multiply this by a constant, because remember you've got real, if you've got conjugate, if your roots occurring in conjugate complex pairs, then your coefficients, we know our coefficients here are real, so it'd just be a coefficient, a real number times your power would just be the same as the conjugate of a sub n z to the power of n, etc. Okay, now using this, so that's using this rule here, conjugate of z1 times z2, the conjugate of all of that is conjugate of z1 times conjugate of z2, so that's using that rule. And then we know that if you add individual conjugates here, that it's the same as the conjugate of the addition of all of them, so that's using that rule up here. So this is the conjugate of all of that. Now we know that that equals 0 from up here on the first line, that all of this equals 0, so the conjugate of that is 0, which equals 0, therefore the conjugate of z is also a root. So that's the proof for proving that if z is a root, then the conjugate of z is also a root. Okay, now, example 1 says that the polynomial z cubed minus 7z squared plus 25z minus 39 has 1, 0 equal to 2 plus 3i, right? It's 3 linear factors. Now, we know that the coefficients of the polynomial are real. So the coefficients of the polynomial of that polynomial are real numbers. Therefore, by the conjugate root theorem, theorem, 2 minus 3i is also a root. So therefore, we can say that z cubed minus 7z squared plus 25z minus 39 is equal to, remember there will be three, this is z to the power of 3, there will be three linear factors. And so far they are z minus 2 plus 3i. Then we've got z minus 2 minus 3i. And my last, sorry, I've taken up too much room there. And we've also got z minus k. I'll just get rid of this bit here. We've also got z minus k, which is notice as the polynomial. So as the polynomial is degree 3 and therefore has 3 roots. That's why we can write this out as a product of 3 linear factors. Now, just expanding this, I've got, so if I expand these two brackets, I've got z squared minus z times 2 minus 3i minus z times 2 plus 3i, and then times 2 plus 3i times 2 minus 3i. So I'll just expand that. Okay, so I've got z squared minus z times 2 minus 3i minus z times 2 plus 3i. Then we've got a negative times a negative gives me plus 2 plus 3i times 2 minus 3i. So we've expanded these first two brackets. Sorry, I'll just move this over. And then we've also have not multiplied by the z minus k here. Okay, so just collecting some like terms here again. We've got z squared minus 2z plus 3iz minus 2z minus 3iz, so these cancel, plus, this is a difference of 2 squares, so plus 4 minus 9i squared, which is plus 9, so we've got plus 4 minus 9i squared, which is 4 plus 9, and also times z minus k over here. And just collecting like terms here, we've got z squared minus 4z plus 13 times z minus k. Now, if we look at our polynomial up here, it's z cubed minus 7z squared plus 25z minus 39. This constant term will come from multiplying this plus 13 with this minus k. So by inspection and equating constant terms, we know that 13 times negative k is equal to negative 39. So therefore we can see that k is 3. And so therefore z cubed minus 7z squared plus 25z minus 39 is equal to z squared minus 4z plus 13 times z minus 3. But to write the 3 linear factors, remember you can see the linear factors up here, it's z minus 2 plus 3i, z minus 2 minus 3i times z minus 3. So that's writing the polynomial as a product of its 3 linear factors. Now, the other way of finding this third root is to do sum of roots, okay? Or to find the third root, we can go sum of roots. Now we know that one of the roots is 2 plus 3i, the other root is 2 minus 3i, and the other root we'll just call k. We know that sum of roots equals minus b on a, so it's negative 7 on 1. So it's, in other words, we've got 4 plus k, so we've got that 4 plus k is 7, and so therefore k is 3. So that was the other way of finding the third root, that it's 3. Okay, so then you then go back up here after doing that and say, therefore, to factorize it, writing it as 3 linear factors, you'd have z minus 2 plus 3i, z minus 2 minus 3i, and z minus 3. Okay, so that's the end of page 6. We'll now go to the next example. Okay, now this is page 7, example 2, and the question is if a plus ib and a plus 2ib are two zeros of this polynomial x to the power of 4 minus 12x cubed plus 59x squared minus 138x plus 130, find a and b. Now we know that the coefficients of the polynomial are real. So as the coefficients of the polynomial are real, therefore we can say by the conjugate root theorem, so by the conjugate root theorem, we know that a minus ib and a minus 2ib are also roots. Now what we can do here is sum of roots, product of roots. So the sum of the roots is a plus ib plus a minus ib plus a plus 2ib plus a minus 2ib, and that equals minus b on a. So adding these, we've got 2a, 4a. It looks like 4a. Now negative b on a is negative 12 on 1, which is 12. And so therefore we get that a is 3. So here we've just found a. Now to find b, let's try product of roots. So we're going to do the product of the roots, and that's a plus ib times a minus ib times a plus 2ib times a minus 2ib is, so we've got minus b, c, minus d. It's e on a, so that equals e on a, which is 130. Sorry, just running off screen there, which is 130 on 1. So these are a difference of 2 squares, so this equals a squared minus I squared b squared, which is plus b squared. And this also is a squared minus 4i squared b squared, which would be plus 4b squared. And that is equal to 130. Now we know that a equals 3, so a equals 3, so therefore substituting that in, we get that 9 plus b squared times 9, so these are a, 9 plus 4b squared is equal to 130. Now we can expand that and take everything over to the left and refactorize. So we've got 81 plus 36b squared plus 9b squared, which is 45b squared, plus 4b to the power of 4 minus 130 equals 0. So we've got 4b to the power of 4 plus 45b squared minus 49 equals 0. So factorising this, we've got 4b squared. Let's try, now we need the factors of negative 49. Well, actually we won't do it like that. We'll do 4b squared and b squared. I think if we put the 49 here and the 1 there with a plus and a minus, we should get 4b to the 4 plus 4b, sorry, minus 4b squared plus 49b squared minus 49. Yes, that factorization works. Now, so therefore, we've got that 4b squared plus 49 equals 0. That has no real solution. So that's got no solution, no real solution, because we need a and b are real, okay? And we've got that b squared minus 1 is 0, therefore b is plus or minus 1. And so therefore our roots are, so find a and b, we just have a is 3 and b is plus or minus 1. So we've got that the roots are a plus ib would be would be 3 plus I, so that's your first root. Then a minus ib would be 3 minus I. Notice if b is plus or minus 1, that's how you're getting the result for a if b is 1, you get 3 plus I, and if b is negative 1, you get 3 minus I. So that takes care of the roots there. And the other ones are 3 plus 2i, because the other roots are a plus 2ib, and 3 minus 2i. So they're your 4 roots, but we've found a and b. Now we're asked to fully factorize this polynomial. So therefore our polynomial in x is x minus 3 plus I, because we've got those roots there, x minus 3 minus I, x minus 3 plus 2i, x minus 3 minus 2i. And just expanding, opening up these brackets, we've got x minus 3 minus I, x minus 3 plus I, x minus 3 minus 2i, x minus 3 plus 2i. And that's the full factorization of our polynomial. Okay, now this is a question from the exercise, so it's from exercise 3.2, it's question 16. And the question is to find the real numbers k such that, I think, z equals ki is a root of this equation z cubed plus 2 plus iz squared plus 2 plus 2iz plus 4 equals 0. Hence, or otherwise, find the 3 roots of the equation. There would be 3 roots because it's a cubic. Notice that that the coefficients are not real, so the roots will not be conjugate pairs of each other. So we have to find the real numbers k such that z equals ki is a root of the equation. So if ki is a root of the equation, then we sub ki into the equation and we use the factor theorem. So sub ki into the equation, and we'll know that p k of I equals 0 by the factor theorem, okay? So we get, if we put ki in here, where z is, we get k cubed I cubed plus 2 plus I times, now z squared will be k squared I squared. And then we've got plus 2 plus 2i times ki plus 4 is equal to 0. So we know that I squared is negative 1. So we'll get negative I k cubed. Here I squared is negative 1, so we'll get minus, and I'm going to expand as well. So we get minus 2k squared minus ik squared. And we're just going to expand here. And we've got plus 2ki. Then we've got plus 2ki squared, which is minus 2k, plus 4 equals 0. And just seeing if we can get these in some sort of order. I'm going to go for my highest power of k squared there first. Actually, I think we should group the real and the complex bits of the of this together. So let's put and we've got a lot of negatives here, so let's take things over to the other side. So we've got 2k squared, positive 2k squared, then we've got plus 2k minus 4. So what I'm doing, I've taken the 2k squared to the other side, the minus 2k over, the plus 4 over, and doing the same with the I terms. Now I've got plus ik cubed, moving this one over, plus ik squared minus 2ki equals 0. And so our real part, and we're going to factorize this, so we've got 2k squared plus 2k minus 4 plus I times k cubed plus k squared minus 2k equals 0. So now what we're going to do, equating real and imaginary parts. Now we know if z equals ki is a root, then this first part here must equal 0. Okay, so we've got that 2k squared plus 2k minus 4 equals 0. Dividing through by 2, we've got k squared plus k minus 2 is 0. Factorising this, we've got k plus 2 times k minus 1 is 0. And so therefore k is negative 2 or 1. Now for this whole thing to equal 0, this real part has to equal 0, but the imaginary part has to equal 0 if this substitution is going to equal 0. So therefore, we've also got that k cubed plus k squared minus 2k is equal to 0. Factorising out a k, we've got k times k squared plus k minus 2 is 0. This factorisation, again, is k times k plus 2 times k plus 1 is 0. We know that therefore k is 0, negative 2 or 1. Now, but k cannot equal 0 as 0 is not a root of the equation. Because if we have a look at the original equation, if you put 0 in here, okay, you'll get 0 plus 0 plus 0 plus 4, that does not equal 0, okay? That is because p of 0 does not equal 0, okay? Now, so therefore, k equals negative 2 or 1. And so therefore, two roots of the equation are I and minus 2i. Because we know that the roots of the equation are ki. So we need to find the third root. So let the other or third root equal alpha. Now by sum of roots, we know that I plus minus 2i plus alpha equals, sorry, that's off the screen. So by the sum of the roots, I plus negative 2i plus alpha equals negative b on a, which is negative 2 plus I over 1, which means that alpha minus I equals negative 2 minus I, which means that alpha equals negative 2. And so therefore, the roots are I, negative 2i, and negative 2. Okay? Now let's just, so therefore, if we do p of negative 2 here, in our original equation, that should be a solution. Okay? So, I mean, we can try that if we want. So you would get, I'll just do it over here as a checking. You don't have to do this, but I'm just checking it just to show you. So checking, let's look at p of negative 2. Substituting z is negative 2. We get negative 8, and this would be 4 here. So we get plus 4 times 2 is 8. 4 times I is 4i. If this was negative 2, if z is negative 2, we'd get minus 4, and then we'd get minus 4i, and then we'd get plus 4. And if we look at all this, negative 8 plus 8 cancel, 4 plus 4i minus 4i cancel, and minus 4 plus 4 cancel. And we can see that negative 2 definitely is a root of the equation. And we saw here that the other roots are I and minus 2i. Okay? So they're the roots of the equation. That's the end of that question there. Okay, now this is example 4 on page 8 of the Polynomials booklet. P of x is a monic polynomial of degree 4 with integer coefficients. So therefore, that means that you'll have conjugate roots, okay? And it has a constant term of 2. P of x has a 0i, and it also has a rational 0. So it has this complex 0 and a rational 0. The sum of the zeros of P of x, is a positive real number. Find P of x factorized into irreducible factors over the real numbers. Okay, that P of x, so P of x has real coefficients. So therefore, we know that I is a 0, so P of I equals 0. P of minus I is also equal to 0 by the conjugate root theorem. So by the conjugate root theorem. Okay. Now, so therefore, if we just start factorising, we know that so far x plus I times x minus I, these are two factors, okay, of our polynomial. Remember, it's got degree 4. So we know that x plus I times x minus I, they're two factors, okay? And that's equal to x squared minus I squared, which happens to be x squared plus 1, is a factor of our polynomial in x, okay? Now, because we know that this is a monic polynomial, we can say, therefore, well, our polynomial in x, because it's monic, is x squared plus 1, so that does these two factors, times x minus alpha times x minus beta, okay? Now, we can only write this, for example, because we know it's a monic polynomial. So that's why we can write it like that. Otherwise, we'd need to write one of the factors like 2x, 2a minus b, or something like that, okay? Sorry, I mean ax minus b, beta, or something would have to be one of the factors. But because it's monic, we can write it this way: x squared plus 1, x minus alpha, x minus beta. Okay, where the rational zero of alpha takes on values of either plus or minus 1 or plus or minus 2, since P of x is a monic polynomial of degree 4 with a constant term equal to 2, okay? So let's look at product of the roots. So we know that product of roots, or if we just look at the constant term, I suppose, don't have to write it as product of roots. I'm just going to put that our constant term we know is 2. So our constant term will be 1 times minus alpha times minus beta, will be 1 times minus alpha times minus beta, which equals 2. In other words, alpha times beta is 2. So we know that alpha times beta is 2. So, therefore, we know that the zeros of P of x have to be I minus I. We can have 1 and 2, giving alpha times beta is 2, or I minus I, negative 1 and negative 2, because negative 1 times negative 2 will also give 2. But we're told that the sum of the zeros is a positive real number. So, but I plus minus I plus the two other roots plus alpha plus beta are greater than 0. So therefore, the roots must be I minus I, positive 1 and positive 2. Okay? Because the sum of all those, so therefore it must be I plus negative I plus 1 plus 2, which gives us 3, which is greater than 0. So the roots can't be negative 1 and negative 2, the other two roots. So therefore our polynomial in x, if we write it in a factorized form into irreducible factors, see, x squared plus 1 can be reduced, so that's not an irreducible factor. So the polynomial in x will be x plus I, x minus I, because we know that that's where we got our x squared plus 1 from, and we've got x minus 2 and x minus 1. Okay, so that's our polynomial in x, written as irreducible factors over the real numbers here. Okay, so, so they're factors and they're irreducible over the real numbers. And these factors are irreducible over the real numbers, so are irreducible over the real numbers. Now, example 5, we're using the remainder theorem here. Now it says find the remainder when this polynomial in x is divided by x plus I. Remember that written in as a factor is x minus negative I. So what we're doing, we'll look at the p of negative I, and we're using the remainder theorem. So p of negative I here is negative I cubed plus 2 times negative I squared plus 1, which is negative I times I squared. Well, it's negative I times negative 1, or negative 1 times negative I, plus 2 times negative I squared is I squared, which is negative 1, plus 1. So we've got I minus 2 plus 1, which is, sorry, that's 1. So I minus 2 plus 1 is I minus 1. So that's the remainder when this polynomial is divided by x plus I. Now, if we divide this polynomial by x squared plus 1, then we know that our polynomial in x, which is x cubed plus 2x squared plus 1, would have to equal x squared plus 1, some polynomial qx plus rx. This is the division transformation, that if you divide x squared plus 1 into this, just pretend we're doing this, x squared plus 1 is divided into your polynomial x cubed plus 2x squared plus 1, then you'll get your quotient up here, but then you'll get a remainder down here if you did the division, the long division. So therefore your polynomial is x squared plus 1 times qx up here, the quotient, plus whatever you get down here if you were doing the division, which is the remainder. Okay, so we can write this out like this. Now we need to try and work out what our remainder here is, and I'm going to write this as x squared plus 1 times my quotient q of x plus the remainder ax plus b. Okay, because it could have a degree of 1. Okay, so if I just try and work out what substitution of x I can do here, I know that, for example, if I can make this x squared plus 1 equal 0, then I'll wipe out this term and I'll be able to probably do some equating here and work out what a and b are. So if I just put x squared plus 1 is 0 and work out a value of x that will make that 0, I get that x squared is negative 1 and therefore x is I. So if I do p of I, if I substitute I into here, I get I cubed plus 2 times I squared plus 1. And if I put x is I in here, I get this becomes 0, or this becomes 0, plus I get, if I'm doing x is I get plus ai plus b. So I cubed we know is I squared times I, so it will be negative 1 times I, which is negative I, and plus 2I squared is minus 2 plus 1, which is minus 1, is equal to ai minus b. And if we equate coefficients, therefore I can see that a is negative 1 and b is positive 1. Sorry, I've just written this out wrong. This is ai plus b. If we substitute x is I get ai plus b. So therefore equating, I get a is negative 1, b is also negative 1. So therefore my remainder will be ax plus b. So therefore the remainder in x is ax plus b. So we know that it's ax plus b, and we know that a is negative 1, so we get negative x, and b is negative 1, and we get minus 1. So therefore my remainder is negative x minus 1. Sorry, just can't see that. So remainder, remember, is ax plus b. We know that a is negative 1, so we get negative 1x, and b is negative 1 minus 1. So your remainder is negative x minus 1. So now for this last example, example 6. It says when your polynomial in x, which is this, x to the power of 4 plus ax cubed plus 3x minus 11, is divided by x squared plus 4. The remainder is x plus 5. Find the value of a. So similar thing, we're going to do the remainder theorem again, but we're just going to see what's going to be good to substitute. Okay. Now, again, using the division transformation. I'm just going to write this up the top. Our polynomial in x, of course, is ax times qx plus your remainder rx. So, my polynomial in x is x to the power of 4 plus ax cubed plus 3x minus 11. It equals x squared plus 4, which is your divisor, times your quotient plus the remainder. And we know that the remainder is rx, but we actually know what the remainder is x plus 5. Now again, looking for something to substitute. If we can wipe this out and make this 0, let's just put x squared plus 4 is 0. So x squared is negative 4. We know that 2i squared will equal negative 4. Because 2 squared is 4, I squared is negative 1. So therefore, we've got that x is 2i. Actually, we can just write here that x would be the square root of negative 4, which is, the square root of 4i squared. That's probably easier, which is 2i, okay? So we want to do p, we want to use the remainder theorem and substitute 2i in there. So we've got p of 2i, so we'll substitute 2i in here, and we'll get 16i to the power of 4 plus 8i cubed a plus 3, we'll get 6i minus 11. Now, if we substitute x is 2i, this will all wipe out. And remember, our remainder, we know is, so we'll get 0 plus our remainder, this remainder is x plus 5. So I might just actually wipe that off and just go x plus 5 here, because we know that the remainder is x plus 5. And just working out what this is, 16 times I to the power of 4. I squared is negative 1, so it's negative 1 times negative 1 is positive 1. And we get 16. And we know that I cubed is negative 1 times I, which is negative I, so we've got minus 8ai plus 6i minus 11 is equal to, remember we're substituting x is 2i, and we get 2i plus 5. Again, collecting like terms, we've got that 16 minus 11 is 5, and that equates with our constant. And we've got plus I, 6 minus 8a is equal to 2i plus 5. So equating real and imaginary parts, therefore equating imaginary parts, we get that 6 minus 8a equals 2. So 8a equals 4, or a equals a half. And that's that solution. So it says when that polynomial is divided by x squared plus 4, the remainder is x plus 5. Find the value of a, and we've just worked out the value of a.